Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into section 6.3 in the Big Ideas Math Integrated Math 3 textbook. We are multiplying and dividing rational expressions. Now, coming up next in 6.4 is adding and subtracting. Multiplying and dividing is actually easier. If you think of rational expressions like fractions, I like multiplying and dividing fractions a lot more than adding and subtracting, especially if I have to find some sort of common denominator. We'll do that in 6.4. 6.3, we don't have to use those rules, right? We can skirt by those, no common denominator necessary. There are some things we're going to have to do, and it also involves knowing how to factor again. Common factors, quadratic factoring, probably even sum and difference of two cubes. We'll see what shows up there. Jump to the description section down below to find the PDF of this set here, the problem set in all. We're going up to problem number 49. You can also find the timestamps down below as well. I don't believe there's anything that we do have to graph, so we got to copy down some problems and do a lot of factoring, a lot of writing to be had, but I'm prepared if you're prepared. Let's take a look at the lecture portion right now. We're going to simplify rational expressions and multiply and divide them. Now, we'll talk about dividing when we get there, but we are going to want to turn that into multiplication, multiplying by the reciprocal. That's actually one of the words down here. That's why I brought it up. And simplifying is just, we want to make sure that we divide things correctly, that we don't cancel things incorrectly. And I quote canceling, I've probably talked about that before, but canceling is not an actual math term, and people misuse it. People incorrectly divide, so we'll see that we can do them correctly here. A rational expression is a fraction whose numerator and denominator are non-zero polynomials. The domain of a rational expression excludes values that make the denominator 0. Now, I don't know if they use the word, I tend to use the word restrictions. They might say exclusions. There should be a plus or minus here as well. A rational expression is in simplified form when its numerator and denominator have no common factors other than plus or minus 1. Here's the proper phrasing we're looking for here. Common factors. It's not just because you have some identical term on top and bottom, you can cross them out and therefore they cancel. That's not how maths. Order of operations dictate something otherwise. So, got to be very careful. So, in cases like these, it says let A, B, and C be expressions. B and C can't be 0. A times C over B times C, the C's can cancel out because C divided by C is 1. And when multiplied by this A and B together, multiplying something by 1 doesn't change its value. So these C's can indeed cancel out. They can cross out. We can divide them, make them 1, and make this appear just as A over B. And these are equivalent expressions in almost all facets. There are things we're going to talk about regarding restrictions or exclusions. I don't know what phrase they're going to say here. But that in mind, let's keep moving forward. Here's another example, 15 over 65. There's a common factor of 5. Now, we tend to say divide top and bottom by 5, and that's fine. You're reducing the fractions that way. But the very fact that there is a common factor of 5 on top and bottom is what allows us to divide them, make them 1, and leave this to 3 over 13, which is equivalent to 15 over 65. Same thing with this expression here, and this is what we're going to be dealing with in these polynomial sets of rational expressions. If I have a common factor of x plus 3 on top and bottom, I can divide, cancel them out, and then I'm just left with this 4 over x plus 3 here, but it's only because it's set up that way, okay? Because there's a common factor on top and bottom, and that's what we're going to be seeking, actual quantities, which can cancel and become 1, etc., that kind of thing. That's what we're looking for. Case in point, we have this scenario right here, x squared plus 7x over x squared. Can I cancel out these x squareds? No. No, you cannot. These are not common factors. That isn't a term on top and bottom that's added. If I had 2 plus 7 over 2, can I cancel out the 2's and make that 7? No. Could I even turn these into 1's and do 1 plus 7 over 1? No. That's not how that works. So, no, we don't do that way. For products, sure. Common factors, yes. So, if you seek a common factor, factor out an x on top, they split these x's on bottom to truly show that these two x's cancel. I'm probably not going to do that. But these can now divide out on top and bottom. You're left with x plus 7 over x, which, by the way, these x's cannot cancel for the same reason the x squareds here could not cancel. So this would be the simplified version of what we have. They did not mention any restrictions yet. I want to make sure you know. Oh, take a look. Down here, they just showed the same thing. X minus 6 over x minus 2. You can't just cancel the x's out and make that negative 6 over negative 2. The book is very well on what's the phrase? Like they have their thumb in the right area to explain this the right way. Gosh, what's the phrase? They have their finger on the pulse. Thumb. they have their finger on the pulse with regards to what mistakes students make. And I want to dispel all this right now. Same thing with these x squareds. Can't cancel them. Nope, doesn't work that way. So I need to keep stressing that. And I hope this doesn't have some sort of Streisand effect thing where suddenly you start doing it just because I told you not to, right? We look for common factors. So let's start doing some simplification. There's nothing to do with multiplication and division just yet. X squared minus 4x minus 12 factors to this guy. I'm not going to reteach you how that is. I'm actually going to go straight into the factoring on them, guys, to be honest. X squared minus 4 factors into this guy here. Now you have an x plus 2 on top and bottom that can, if you want to use the word cancel, that's fine. They divide out, but they cancel. And you're left with x minus 6 over x minus 2. Now, they're mentioning something here. It says x can't equal negative 2. That's a very important thing to make mention of. So this is where we start talking about restrictions. Okay, they do say the word restrict here. So hopefully that's the phrase that they use. Restrictions. Restrictions are values of x that you cannot use because you would be dividing by 0. You might say, Mr. Robinson, if I substitute negative 2 into here, I get negative 8 over negative 4. That's 2. That's not division by 0. There's no problem there. There was earlier. Is x plus 2 over x plus 2 right here? What if I substitute negative 2 into here? Well, now you're going to say, Mr. Robinson, it doesn't matter. They canceled out. No, they didn't cancel. They divided to become 1 because any non-zero number over itself is 1. But what happens when you divide 0 by 0? You get an indeterminate. You don't get 1. So what if x is negative 2 in the original? This is what matters. The original expression. We may be simplifying it, but we are simplifying it for all cases of x except where x can't equal negative 2. So what we're saying is that this is equivalent. This is equivalent. Oh my goodness. This is equivalent to this original expression, but we have to note that, hey, if we're negative 2, that's a problem because negative 2 would have been a problem up here. And that's what we're doing with some form of restriction. So the original expression is undefined when x equals negative 2. To make the original and simplified expressions equivalent, you must restrict the domain of the simplified expression by excluding negative 2. They're both defined when x equals 2, so it's not necessary to list it. Interesting. I always thought it was necessary to list those restrictions regardless, so I'm surprised that they don't actually say that here. I did need to read this to ask why they didn't include 2. I feel like I need to include it. We'll see what they talk about later by not including those. That's actually very interesting. I did not expect that. I'm used to, with my students, stating all restrictions, what x can't be, because that helps us talk about, listen, we just came off graphs. Clearly, if we talked about graphing this thing, x can't equal 2. That's part of our domain restriction issues, right? Because there we have a vertical asymptote. Here at x equals negative 2, we technically have something called a hole. We're not talking about graphs in whole as a whole entirely, but I wanted to bring up any such restrictions. X can't equal negative 2, can't equal positive 2 either. Anyway, we'll see if they end up expanding on that a little more. I'm curious. Okay, multiplying rational expressions. The rule is the same as rule for multiplying numerical fractions. Multiply numerators, multiply denominators, and write the new fraction in simplified form. Easy. I mean, simple enough. Better than addition, actually. So, a times b over c times d is a times c over b times d. That makes sense. Which is really a way of stating that a is not just dividing by b, guys. Because it's multiplying by the fraction, a is always dividing by d. Now, they join these two things together. I tend not to. It's just because probably it's just one extra step, so I tend not to do it. So when they find things that they're canceling here, by the way, they're seeking common factors for reduction. I reduce 30 over 20 to 3 over 2 like that. I won't factor 10s out to make them so, but it's cool that they're showing it because it exemplifies when common factors can cancel. So I'm good with them doing it. But they're kind of joining up x's into x cubed here, and then they split out in x because it's going to cancel with that x here, things like that. Anyway, you simplify it, and it becomes 3x squared over 2. But they stated some restrictions. X and y each can't equal 0. How come? Because the original expression had x's and y's in the denominator such that if either of them were 0, you would get 0 out as a result, despite the fact that there are no x's and y's in the denominator once simplified. Just because they canceled doesn't mean that we're not talking about the original expression still, and that's the goal. I want to see what they're doing here. I can't tell. It just looks like another example to me. Oh, this is this bottom one. Okay. Find the product here, multiplying these guys. Again, what I tend to do is I tend to simplify things first. That's probably what they're mentioning. Okay, they're saying you could first simplify each rational expression and then multiply it and then finally simplify it. Yeah, I would totally do what they did up here. 8 over 2 simplifies to 4, x cubed over x simplifies to x squared, y over y squared is a y in the bottom, that kind of stuff. I would tend to simplify first before multiplying. Heck, I would keep simplifying, like 4 over 4 right here. Boom, is 1. Y squared over y. Boom, is y. Things like that. I would work more that way personally. That's just me. They do show restrictions. Here's just another example of more of the same. Again, they joined them up together in multiplication. I don't tend to do that. They show once again, one simplified with everything, whether you did this version or that version, that x and y can't equal 0 for the same reason that they existed in the denominator, in such a way that plugging in 0 would make them 0. Now, I need to stress that it's not that x and y can't ever be 0. It's that the denominator can't be 0. So we already saw a previous expression where it said like x plus 2. So it's not that x couldn't equal 0. X couldn't equal negative 2. Negative 2 is the value that would give us 0. Here's another example with just more. So the first thing I would do, guys, is I'd factor. I would do any sort of factorization that I can do and clean things up where I can. You can treat these as one entire fraction, like this, boom, 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 or as separate products still. I tend to keep them separate just because there's no reason to do it or not to do it. I just do. But 3x is a common factor here. I would argue negative 3x is a common factor. Actually, they're going to get into that in a moment. This factors into this guy, and this factors into that guy there. Now, me personally, I'm already seeing these x plus 5s and canceling them out, things like that. And the 3x's, I'm canceling them out. Yes, I'm saying the phrase canceling. Now, 1 minus x and x minus 1 are not the same quantity. So they would not cancel out here. However, it looks like they do something here in a moment. Take a look at this 1 minus x. And take a look right here where they have negative 1 times the quantity x minus 1. So they make their leading term, that x, which was negative. They factored a negative out, and then they have the x minus 1. So now negative exists on the outside with the x minus 1s, now canceling. You can see it down here where they cancel. They do the x plus 5s and 3x's there. And then you're left with a negative 1 multiplying by the x minus 4, and they seem to want to distribute afterward. And they show all these restrictions here, what x isn't allowed to equal, based on what the denominator shows. This was in a pre-cancellation set. X couldn't equal 1 or negative 5 or 0 because those are what would give you 0 in the denominator at some point. They even show that here. They show, my face is in the way, but negative 5 and 0 and 1 when substituting or when inputting the original expression lead to errors. Whereas when simplified, it leads to these values, but you can't go off the simplified expression. It's just, remember what simplification means. Dividing common factors on top and bottom that would lead to 1 if it weren't for these x values here. Okay, let's get into, I thought this was going to be division. Multiplying by a polynomial is nothing other than putting this number over 1, so I'm going to leave this into what it is. This is a difference of 2 cubes down here, which if you recall is a cubed minus b cubed factors to a minus b times a squared plus ab plus b squared, so they do that here. And then these happen to cancel out there. Now, they didn't mention, I guess they're mentioning it right here, but x squared plus 3x plus 9, it's actually not possible to get a real solution out from that one. We're not talking about the imaginaries in graphing form, so there are actually no restrictions on x with regard to this set here. There's a restriction here where x can't equal 3, and honestly, it bugs me that they're not stating those restrictions. I guess I'm going to have to marry to what they do, but I'm stating this in an out loud sense. It bugs me. I don't know. I think I'm still going to state them. It's part of my domain restrictions. Maybe I'll stress that these are my vertical asymptote restrictions, and then anything that would be here, which I can't get anything there, would be my whole restrictions. But the bottom line is we're not graphing now anyway. But it bugs me that they're not stating it. I don't know. I get it. I think they're just saying it's implied. We can come up with that and understand it. I get it. Because we couldn't come up with ones that would exist from here if they're gone. But it's just something that I have in old videos, so it's just weird that it doesn't show up here. Anyway. All right, let's do the division. I mentioned this before. Division of a fraction means multiplication by its reciprocal like this. So it's very straightforward, guys. You just got to flip this second guy, and then you multiply and go to town with it. The one thing about it, though, is that previously d was in the denominator. Even if it flips over later, it was a denominator value. And guess what? Now c is a denominator value as well. That means that b, d, and c, whatever quantities they are at one point or another denominator values. Why is that important? Restrictions. What was 2x minus 3 in this beginning example when it shows division here? This was in a denominator. Just because it flips over and goes in a numerator doesn't mean it wasn't in a denominator at some point. That means we have to note this restriction that 2x minus 3 can't equal 0. Whoopsie. 2x minus 3 can't equal 0, so 2x can't equal 3, therefore x can't equal 3 halves. And they're pointing that out to you right now. They're saying x can't equal 3 halves, and that's something because of the fact that it was once in the denominator. B, C, and D can't equal 0. Why can't C equal 0? It's in the numerator, because it does flip at some point, and it does go in the denominator. Now, why don't they mention it? Because that was their choice. They're deciding to state that if it's something in a denominator at the end, it's implied that we know those are domain restrictions. I get it. I get it. But x can't equal 3 halves. By the way, nothing's simplified. Like, nothing canceled. It just is what it is. You keep things factored as you can. Anyway, that was an example within. So let's take a look at this full one where they do the flip first. I'm trying to decide whether I like factoring first or flipping first. But they do this flip first. Keep in mind, as long as this is division, this ain't dividing by that. This is dividing just by this by this. And yeah, you might want to write it as multiplication before you do anything rash on canceling. Be very careful. Common factor of 2, common factor of x. This is x minus 5 times x minus 6, yada, yada. These ones cancel, and more, right? Lots of things going. Mayhem. You end up with 7 halves, which is interesting. A lot of things cancel except the 7 and the 2. But hey, x can't equal any of these 3 things because it can't equal 5 from down here. It can't equal 6 from here, 0 from here, or 6 from where it originally was, or 5 from where it originally was. Anything that canceled, it can't be. All those would actually have holes for this graph. All right, dividing by a polynomial, same thing. This is something over 1. So you can also flip that thing when you multiply, make it 1 times that thing. I'll let the example do what it does. You can take a look at it regarding factoring. We are going to have to factor some more advanced quadratics, I suppose. So it's something we did of the past. It's not something we can't do again. You're left with this simplified expression. No, these x's can't cancel. X can't equal negative 5/3. How come? Because the canceled set here, 3x plus 5 can't equal 0. And so on and so forth. This guy's judging us right here. Let's keep moving downward, solving a real-life problem. The total annual amount I in millions of dollars of personal income earned in Alabama and its annual population P in millions can be modeled by this. I equals this guy. What's T represented? The year. I and P, where T represents the year with T equals 1 corresponding to 2001. It says find a model M for the annual per capita income. Per capita means per person. I don't know why they don't say per person, but it does mean per person. Estimate the per capita income in 2010. So we are going to be dividing the income by the per capita, by the population here. I divided by P, and they write it out as such. And this is a good instance of why this over 1 thing matters for this case. So they flip the fraction, multiply by the reciprocal. I don't see common factors of sorts. I don't really know what they're doing with it. They said estimate the per capita income in 2010 because T equals 1 corresponds to 2001. So 2010 is 10 years later. So we do a substitution. Nothing really simplified, but 34,707 is the approximation. That's the per capita income in Alabama, $34,707. All right, that's the end of the lecture portion. Let's go to the vocabulary and core concept check, and then we have numbers 3 through 49 to take care of. I'm still, in my mind, for the past 5 minutes, I've been struggling in between as to whether I mention the restrictions on the things that are on the bottom by the end or not. Maybe I just follow the book and I make mention of them. Maybe I just do that. All right, number 1 on writing, describe how to multiply and divide 2 rational expressions. Well, division is multiplication by a reciprocal, so I'll just mention that to begin with. So that way they're the same. Is multiplication of the divisor's reciprocal. Oh, I can't remember. Divisor's reciprocal. I think it's called the divisor. I don't want to be wrong, but I think it's the divisor. Multiplication. See, what we're not doing in multiplication, guys, is our goal isn't to like FOIL and distribute. No, we want to create factors. Multiplication stems initially from seeking common factors. Excuse me, from factoring. Yeah, from factoring polynomial expressions. And then canceling common factors in the numerator and denominator. Noting their restrictions in the simplified expression. Because once they cancel out, and I get it, so once those ones cancel out, I get why we have to note those ones for sure. We absolutely should. Those ones that are gone, make note that they never could have been. Yeah, so we got to note it. Which one doesn't belong? Which rational expression does not belong with the other three? Explain your reasoning. In the first one, I have x minus 4 all over x squared. I don't know what that is yet. I'm just going to mark that an A. I wonder if the... I don't know. This one factors into this. This one factors into this. It has something to cancel. Maybe it has to do with cancellations. 9 plus x over 3x squared is nothing to cancel. This one has x minus 4 times x plus 3. And this is x times x minus 6. This is the only one that has something that is canceling. So I suppose it's that one that's different. So this one is, there is a restriction. I don't know. There's a hole. There's a restriction. There's a domain thing that's not being mentioned. There's a cancellation. That's all I'm going to mention. That doesn't make it bad. In fact, it makes it better. It could actually be simplified. These ones I factored. That's not simplifying. Cancellation, simplifiable. I call that the good one. I call the A ones the bad ones. All right. I don't know if I spelled simplifiable right. I don't even know if simplifiable is a word. All I know is that guy just cleared that pole vault. Look at that. All right. So we're going to begin. We have numbers 3 through 49 to do. A lot of things to take care of. A lot of old factoring tricks of yore. I might have my own style when it comes to the actual multiplication and simplification of these things. I hope that's okay. If not, go find another solution guide video for this section, shall you? I don't know if it exists. All right. In numbers 3 through 10, simplify the expression if possible. So these don't have multiplication and division just yet. We are seeking common factors on top and bottom to deal with. So this has a common factor. There's a 2x squared still on top, and x can factor out on bottom. You have 3x minus 4. Now here, these x's can eliminate. 1x on top, 1x on bottom. So you're left with 2 over 3x minus 4. That would be the final result. Now, there is a restriction here where x can't equal 0. If x equaled 0 in the original problem, you'd be dividing 0 by 0, which is an indeterminate. That's not allowed. Despite the fact that plugging in 0 in here is not a problem, remember what we're stating, if you missed the lecture, is that these are equivalent to each other in all facets, but we have to account for that equivalency by saying if the original couldn't have x equal 0, then this one is not allowed to have x equal 0. The simplification is that cancellation of those things, but 0 divided by 0 is not 1. And that's the problem. All right, number 4. 7x cubed minus x squared over 2x cubed. This, I have an x squared that can factor on top. And on bottom, I can remove 2x squareds from there. So you're left with 7x minus 1 over 2x. Like so. Now, that would be my final answer. What my mind wants to go to is state that x can't equal 0. And by the way, x can't equal 0. Let's make no mistake about that. Mr. Robinson, what happens? What if I plug in 0 in here? I divide by 0. That's a problem. You're right. It is. What the book seems to stress, if you missed the lecture portion, this is the main time I'm going to pause to say this. What the book tends to mention is that we can make that inference for ourselves. Right? It's implied with this set in denominator that, yeah, you can't divide by 0 here. When we want to make mentions of these things here are for parts that cancel out outright and are eliminated from the simplified expression. The x's that I divided out of here were x's that couldn't equal 0. But when there's still another x that can't equal 0 in the simplified expression, we don't need to mention it. If they asked about domain, yeah, domain x can't equal 0. But they're not. They're talking about restrictions that are not clearly seen in the final answer. So, if you find old videos of mine, and when I'm talking old videos, I mean like 10-year-old videos. When you find like 10-year-old videos of mine where I do state all restrictions, I even call some that are holes, some that are vertical asymptotes based on what we're doing, you will see me mention these x can't equal 0. I'm going to follow the book on this and do what they're doing. All right, let's keep moving forward. This thing factors into x minus 6 times x plus 3. And on bottom, this factors into x minus 6 times x minus 1. The x minus 6's cancel. Sure, that means x can't equal 6. X can't equal 1 either, but hey, we can tell that x can't equal 1 because it's right there. But x can't equal 6 based on the original expression. If I substitute 6 into there, I'd get 0 over 0. I got to be able to fit these problems if I'm going to go left to right like this. Number 6. X squared plus 13x plus 36 divided by x squared minus 7x plus 10. And I mentioned this in the lecture portion, by the way, as well, guys. I'm not going to slow down on the factoring. Factoring is something we've done in IM2. We've done earlier in this, textbook as well. So as long as I know how to factor it, I'm going to factor it straight up. This one, I'm at pause for what this is. X plus 9, x plus 4. And the thing is, generally with simplifying is you're hoping that this has things that will, cancel on top and bottom, right? That something will actually factor it out. In this case here, nothing actually works out on top and bottom. So this can be the answer or this can be the answer. Honestly, if you recognize that nothing can simplify, you do that. Otherwise, I'm just going to box it like here and say it there. If I talked about overall restrictions, hey, x couldn't equal 5 or 2, but we can tell x can't equal 5 or 2, so we don't say it. Notice that's... Sorry, textbook. I am mocking you more than anything else with that. I feel like that's something we should be stating. Big ideas math. You're getting intimate ideas, man. Those ideas are minuscule. They're tiny. They're small. All right. On top, I have x plus 2 times x plus 9. On bottom's the sum of two cubes. It's x squared plus 2 squared. So it factors into x plus 2 times x squared minus 2x plus 4. If you recall how the sum and difference of two cubes work there. X plus 2's can be gone. There is no restriction on this. Even if there was, it's already written in the final result there. But that also can't factor more. I think that's the main thing I want to mention. It can't factor more. So we have this as our final result. And x can't equal negative 2 as a part of what we can't have. Number 8. We have a difference of two cubes on bottom on number 8 and a standard quadratic on top. Okay. Top factors to x minus 3 times x minus 4. Bottom is difference of two cubes of x cubed minus 3 cubed. So it factors into x minus 3 times x squared plus 3x plus 9. X minus 3's on top and bottom can go away. You're left with the x minus 4 over x squared plus 3x plus 9. X can't equal 3 in the original equation. Therefore, it can't equal 3 in the simplified expression either. Okay. Number 9. Ooh, it's big. On number 9, and, I need to stress the importance of this idea, guys, that we can't just cancel terms on top and bottom. We have to cancel common factors. I don't even want to say the word cancel, but it's just the fastest one to say. Instead of divide and become 1. But we have to understand when we say the word cancel what we actually mean by that. On top, I have a common factor. I want to begin with, 2. And then I have x to the 4th minus 25, which is its own kind of difference of two squares. It's quadratic form, even though it's a quartic. On bottom, I can factor by grouping, if you recall how that thing works. Common factor of the first two terms, I get x minus 3. And then I can factor out a negative 5 from the next two terms, I get x minus 3. Still not done on top or bottom, so this is a problem of more things to do. I have x squared minus 5 times x squared plus 5 on top. On bottom, 4x squared minus 5 is this guy here, and this other guy is x minus 3. As far as I can tell, did I screw something up? Oh, I'm sorry. This is 16x to the 4th. I'm sorry, I totally missed that. So 4x squared minus 5, 4x squared plus 5. I was going to say, as far as I'm concerned, nothing's going to cancel. That was great work on factoring and all, but it kind of wasn't, because we factored the 2, it's 16x to the 4th. I guess I got so caught up in talking about x to the 4th, I missed that. Anyway, 4x squared is minus 5. Yeah, those can totally go away there, right? Those are good. So now you're still left with, you can leave this in factored form, 2 times 4x plus 5, 4x squared plus 5, excuse me. How did I get rid of that? 2 times 4x squared plus 5 all over x minus 3. Okay, now, as far as restrictions go, there's a little bit more work to be had. Let's talk about this set. Sure, x can't equal 3, but what else? 4x squared minus 5 can't equal 0. So let's do some work on that. Let's add 5 to both sides. Let's divide both sides by 4. And let's take the square root of both sides. Oh, this is can't equal, can't equal. X can't equal plus or minus square root of 5 over 4. That's square root of 5 over square root of 4, which is 2. Plus or minus root 5 over 2. So that's what this restriction set is here. Those are two different values x cannot equal. A little bit crazier with work, but that's how the work goes. Those are the whole portions that we talk about. Okay, I hope I cleaned everything up right. I apologize for missing some things that I didn't write the first time. I think I fixed it. Number 10. I guess it's a lot like number 9. We have factoring by grouping and some quadratic form quartic. Let's just be careful, be careful on everything I do on factoring. Don't want to make mistakes. One little slip up changes everything. Okay, 27x to the fourth minus 147. Okay, on top, 3x squared is a common factor of the first two terms. 7 is a common factor of the next two terms. X minus 1 is a common factor of both. Part of the factoring by grouping stage. 147 divides by 3, so does 27. So you can factor a 3 out of here. You're left with 9x to the fourth minus 49. So this top is 3x squared plus 7 times x minus 1. On bottom, I have 3x squared minus 7 times 3x squared plus 7 with that extra 3 hanging out there. I got a couple 3x squareds plus 7s that can go away. I'm still left with an x minus 1 on top. So I got x minus 1 all over that 3 times 3x squared minus 7. Now, despite the fact that there is some value of x here, or two different values of plus or minus, that would be restrictions to make 0. Remember, we don't mention them. We would only mention them for the 3x squared plus 7s. However, 3x squared plus 7 can't equal 0. It's never going to equal 0. You're good on this. Or not with real numbers anyway. If I subtract 7 over, divide by 3, I take the square root, taking the square root of a negative. Right? I square any number for x, any real number, it's going to turn positive. There's no way I can get 0 out from that. There are no restrictions on that I need to mention from this cancellation. So we're good. We're good. Okay, numbers 11 through 20, we are to find the product. So it's just like kind of a step behind what we were doing on these other sets. Now, I tend to, and I mentioned this in the lecture portion, I tend to not multiply things out in general. I got to think about times that I will. I will only multiply things out into one fraction when I'm all done doing all cancellation I need. In this original fraction here, this x over this x can go away like that. This y and one of these y's can go away like that. And it's at that stage that I look to see what else I can do. 4 eighths can divide and become 1/2 like this. You know, this can look a little clunky. I get it. There are no more x's on top. As far as I'm concerned, I have a 1y squared times y. That's y cubed. And I have x times 2 times x. So that's 2x squared. So I'm left with y cubed over 2x squared. That's my own personal way of going about it. Now, if you understand here, there are still x's in the denominator, which means the x that couldn't equal 0 still can't. So that's not a thing. But the y went away that was there. So the y can't equal 0 as it couldn't originally. We have to make sure that we note that for the end. Some people note it in the beginning, right? Once they understand, there's nothing to factor in the first two problems, but some people note it in the very beginning. Number 12. 48x to the fifth y cubed over y to the fourth. And I didn't mention in the first one, I mentioned in the lecture portion, but once it's multiplication, anything on top divided by anything on bottom is a division. 48, like this is not just dividing by this. This is not just dividing by this. This is also dividing by this, and this is also dividing by that. That's why I did what I did previously. Y cubed, you know what? That is a good reason to clean these things up. But y times y cubed is y to the fourth. When you divide by that y to the fourth, those are gone. Just gone. I have an x squared. Yeah, I guess there is precedence and reason to kind of take care of these early on. X cubed, and remove 3x squared from there. You're left with, or 3x's up there. You're left with x squared. and 48 divided by 6 is 8. So, assuming you can read what I have 8x squared times x squared, which is 8x to the fourth. And this is dividing by y squared. Yeah, it's not the cleanest appearance. I'm recognizing this now, but I honestly also don't do many problems like this. I think with these problems, I actually probably do merge them together more often when they're monomials. It's when they're the big binomial things like these ones, I tend not to as much because there just ain't much joining to be had from those ones. So I think when I said what I do and don't do, I'm seeing the holes in probably what I wouldn't do. Y still can't equal 0, so we don't have to mention it. The x's go away on the bottom, so x that couldn't equal 0 before still can't. We got to mention that one. Number 13. By the way, guys, you know this. I sight read this stuff. When I talk about this stuff, I reflect and I state, am I doing the best for you? Am I doing the best for you who's watching this? And I hope I am in some way. I can't rewind it. I can't go back, and so I state, do you understand it from here? And I hope we can. Everything is multiplied on top, and everything on bottom, things are dividing right now. X minus 3. There don't need to be parentheses around this x minus 3 for it to still be a quantity. It is, for all intents and purposes, a quantity. So is this x cubed, like that. Or this x squared. We don't need parentheses around them, though, to indicate them as long as there are products involved. So x minus 3 over x minus 3, gone. X squared over x cubed, you're only left with a single x on bottom. This is one of those cases where I don't need to write it kind of as a whole. Now I will, now that I'm multiplying in full. This is x minus 4 times x plus 6. You can leave it factored, that's cool. And this is all divided by just that one x. Now, x couldn't equal 0 before, it still can't now, so we don't have to mention it, but x can't equal 3. That's the one we really need to bring up here. I think we need to bring up both. Number 14. The fact that we didn't get to do graphs with holes is kind of disappointing that we're only bringing it up now and you don't know what it is that they mean graphically. So I also question the order in which this is done. I feel like, would I want to do graphs first or last? I don't know. Okay. Got a couple x cubes on top and bottom. Those can go. X minus 9s can go. That's simple enough. I still got a 3 on bottom. So I have x plus 5 times x plus 8. All over 3. Just like that. The x's that were gone on bottom and the x minus 9 that's gone on bottom means x can't equal either 0 or 9. Couple restrictions there. A couple. All right, number 15. We have x squared minus 3x, etc., etc. This time we actually have to do some factoring of our own before we do the multiplication, and I think that that's... and listen, I don't do multiplication until after I do some cancellation. But we got to do factoring first. Let's make all that work, right? We don't FOIL. We don't distribute. So leave the x minus 2 and the x on bottom exactly as they are. Nothing to factor there. On top, I got a common factor of x, like that. And listen, if you want to write this all as one fraction, be my guest. Totally fine. This is x plus 3 times x minus 2. And let's see if there's anything to take care of. Okay, x on top and bottom. X minus 2 on top and bottom. Nothing's on bottom. That's to say 1 is on bottom, but we don't need to write the fraction anymore. So we're left with x minus 3 times x plus 3. A little difference in 2 squares. But there are still restrictions. X can't equal 0 or 2. Mr. Robinson, I substitute 0 or 2 into here. I'm not dividing by 0. I'm not dividing by anything except 1. Why can't you plug it in? Same thing. It's the original expression that we're writing something equivalent to, but stating what the original expression couldn't have, so this one can't have. Number 16. Just because we simplify something doesn't mean the original isn't considered. Number 16, x squared minus 4x over x minus 1. All right. We have some factoring. Common factor of x on this first guy. And this is x plus 4 times x minus 1 over 2x. Okay, these x's can still go, and these x minus 1s can go. This is a lot like the previous question. There is still a 2 on bottom, though. So this is x minus 4 times x plus 4 all over 2. And no, that 2 has nothing to do with restrictions, even if we were listing them. But x can't equal 0, x can't equal 1. Okay. Number 17. We go up to 20, so 20 must be on the next page. So just more in the factoring realm. It's good to practice these again, and I think it feels rewarding to go, hey, I know how to do this. This is good. X squared plus, not me, but hopefully you guys. X squared plus 3x minus 4, x squared plus 4x plus 4. Already seeing what I want to factor into. Everything's got a factorization. It becomes rewarding when things do cancel and clean up. I get it. It does. You got to still list restrictions. It would feel bad if you factored and nothing cleaned up. So this is x plus 4 times x minus 1. We just saw that on the last problem. And this is x plus 2 quantity squared. Whether you want to write that or separate them, it's probably better to separate, but you can do either. 2x factors here, you got x plus 2. And this is x minus 3 times x minus 1. Okay, anything on top divided by anything on bottom. One of the x plus 2's here and here. X minus 1 here and here. And I think that's it. So not the most rewarding thing, but it's still, it still works. So we have, now I want to front this with 2x. I don't want to write x plus 4 times 2x. I'd rather write 2x times x plus 4 over x plus 2 times x minus 3. X can't equal negative 2 or 3, but that's not what we're talking about. X can't, well, because it's still here, we don't have to mention x can't equal negative 2. X can't equal 1 is the one that we got to mention. Okay, number 18. Seems simpler. Well, there's less to factor. All right, 2x squared plus 2x over x squared plus 5x plus 6. Okay. X minus 3 times x plus 2 up top. On this side, a 2x can factor. You have x plus 1. On bottom, you have an x plus 3 times x plus 2. Okay. X plus 2's. X minus 3, x plus 3. No, you keep those separate. 2 over 4 reduces to 1/2. So that's a 2, and I guess that's a 1. And one of these x's can go away. One of these x's can go away. You're still left with 2 of them there. So if all looks good, I got x minus 3 times 1 times x plus 1. So x minus 3 times x plus 1. On bottom, I got a 2x squared times x plus 3. Now, as far as restrictions go, the only one that canceled that's relevant to us is the x plus 2. So x can't equal negative 2. And say, Mr. Robinson, what about the x's here where x can't equal 0? It still can't equal 0. So we're good. Number 19. We have a product. We have by times a polynomial, not another rational there, but we can just make it something over 1, right? So when it multiplies by that polynomial, by that quantity, just remember that's only a numerator value. X squared minus 11x plus 28. Okay, so the way I'm going to write this here is, this factors into x plus 9 times x minus 4. This is a difference of 2 squares. And this part's over 1. So this thing that factors here is x minus 7 times x minus 4. But it's all over 1. So I got a couple x minus 7s that can go. The x minus 4s cannot. I think that's it. I think that's all that can go away. So I have an x plus 9 on top. And I have 2x minus 4s. Now, I'd much rather write that now condensed into x minus 4 squared like that. And this is all over this x plus 7 times 1. But I don't need to write the times 1. It shows x plus 7 right there. That's the simplified version. At least, well, that's after canceling those out. But x can't equal 7 because of this x minus 7s that canceled. Last one from this set, number 20. We have another multiply by a polynomial. Okay, we will also put that one over 1 as we do all of our factoring. So we got x minus 4 times x plus 3. We got a difference of 2 squares in x minus 4 times x plus 4. And this is times something over 1. 1 is irrelevant again. X plus 4 times x minus 2. Okay. x plus 4s, x minus 4s, and that's it. We're left with x plus 3 times x minus 2 all over 1, or just x plus 3 times x minus 2. There are restrictions from our canceled sets where x can't equal positive or negative 4. I'll just say x can't equal plus or minus 4. Simple enough. Okay. Error analysis. Numbers 21 and 22. Describe and correct the error in simplifying the rational expressions. Well, it pains me to look at this. You can't do what they're doing here. This is just not allowed. Even if they did it, why didn't they cancel out the x's and the x squareds? Because you can't do that. But why do they stick to just these? Okay. I can't get deep into the why of the matter, but we can't do this, guys. It's not about terms. It's not about terms. It's about factors of things that can divide. That's just the order of operations. That's how maths, and this math ain't mathin'. They are reducing fractions from terms that are a part of larger quantities. Therefore, what they are doing is it's forbidden. It's forbidden math. I mean, if I say the word forbidden, that might overemphasize what I'm talking about. You cannot do that. Now, can you simplify something? It depends if there's a common factor. I don't know. So let's take a look. They said correct it. X squared plus 16x plus 48 over x squared plus 8x plus 16. Is there a factorization? Let's find out. X, 12 and 4. And this is x plus 4 quantity squared. So yeah, something can factor because there's a common factor of x plus 4 on top and on bottom. Take away one of those and you have that. X plus 12 over x plus 4. And no, you can't do anything else with this one after. 12 over 4 doesn't become 3. X over x doesn't cancel or become 1 or anything. We are done. So that's what that becomes. Now, the x plus 4 is still on bottom, so there aren't any extra restrictions on top of it. We're good. Okay, number 22, let's describe and correct the error in finding the product. Strangely enough, or interestingly enough, we did not do one with this 3 minus x kind of thing yet, but we're doing it now. Now, what they are showing, x squared minus 25 factors to this, that's good. X plus 5 and x plus 5 on top and bottom cancel, that's good. And then x couldn't equal negative 5. The problem is with this x minus 3 and 3 minus x, and I mentioned it in the lecture portion as well. Those are not identical factors. X minus 3 and 3 minus x are not identical factors. Therefore, they cannot cancel. They can in a way, though. There's a slight thing you got to do. It's just like saying 2 and negative 2 aren't exactly identical. 2 divided by negative 2 isn't 1. Well, it's negative 1. And that's kind of what's going to happen here. So when we do this problem, let's start from the beginning. The very first thing I would do for this part right here, I do not like not being in standard form, right? I'd rather make that thing rewritten so, yes, this is x minus 5 times x plus 5. I'd rather have this rewritten so this does say x minus 3, but you can't just turn it into x minus 3. You got to factor a negative out first, a negative 1. Once I factor the negative out, negative x plus 3 is what we have there. So now it does show up to be the same. It came at a consequence. It's not a bad one. It just came at a consequence. The consequence is factoring out a negative. So a negative exists in the problem now that they factor out, cancel out. And I have x minus 5 on top, negative 1 on bottom. It becomes negative x plus 5. And that's it. Just negative x plus 5. Boom. They had x minus 5, so they're opposite of everything there. X can't, they're correct on the rest though. X can't equal 3. X can't equal negative 5. All that's still good. Yeah, that's it. So that was the one issue with the negative 1. It still needs to exist in the problem. Number 23 on using structure. Which rational expression is in simplified form? Ooh, that's a good question. I guess we have to test all of these out to figure out which one. It's a matter of which ones do and don't have, common factors and such. I'm just going to kind of copy and paste. Actually, you know what? I'm not going to copy and paste them over. If you don't mind, though, I'm going to leave them as they're written and just do some factoring right now. So A is x minus 3 times x plus 2 over x plus 2 times x plus 1. This is not in simplified form because those can go away. So the answer is not A because it's not in simplified form. B has x plus 2 times x plus 4 over x minus 3, or x plus 3 times x minus 1. That one looks to be in simplified form. I can't do anything else with it. And I don't know if that's the only answer, but that seems to be an answer. So I'm going to make sure to note B. I'm going to do C in my head here. X minus 3 squared and x minus 3 times x plus 1. X minus 3 can cancel. On D, x plus 4, x minus 1. X plus 2, x minus 1. X minus 1 can cancel. Yeah, the answer is B. So the answer is B. The other ones have other things that can cancel, right? If there was just one answer, if we knew there was only one answer, there's no reason for me to move forward in writing. On number 24, find the product below by multiplying the numerators and denominators, then simplifying. Then find the product by simplifying each expression, then multiplying. Which method do you prefer? Explain. I personally prefer, for the most part, I personally prefer the second option. When it's monomials, though, I might be bringing myself back into, convincing myself that I like the other. Because here's the thing. I don't do the thing that they do, which is, let me pause for a second. Let me do the methods. First method, which I haven't shown yet, let's multiply things outright. We get 48x squared y to the 5th over 48x to the 5th. And now we can work some things out. These actually divide outright. These go away, and you're left with x cubed right there. So you're left with y to the 5th over x cubed. Let me leave these all in blue. So we have that. Okay. Now, the next version I can do is reduce what's on top and bottom right now. So x squared over x cubed and 4 over 2, etc. We're left with certain things like this. 12 over 24 is 1/2. So now I have 2y over 1x, so x, times y to the 4th over 2x squared. Now if you multiply across, see, this is the part I never do. This is 2y to the 5th over 2x cubed, and 2 over 2 is 1. You have y to the 5th over x cubed. Now, when you guys look at these, you might say, man, there's no, why would I ever do this green one when I could do that blue one? That was so much faster. It depends. Those numbers got bigger. They just so happen to be the same number, though. It's easier to reduce fractions when you have smaller numbers. So what if it was 48 and 196? I don't know what those reduced by. But, something like that, when they were smaller numbers, it might be easier. I don't generally do this part, though, where they multiply across. You've seen me do more of that, hey, the 2's cancel here, and, well, I guess that's it. Hey, the 2's cancel there. So I don't merge first. That saves me a step. Gets a little clunky, gets a little disorganized. But this is in the monomial sense where more things can merge together and multiply out, whereas that factored form of polynomials doesn't have it as often. So this one, for this problem and many monomial problems, multiplying first may be preferred, which goes against what I was saying. However, with polynomials and factoring, I tend to not join. See, here's the thing. They're talking about multiplying things together, literally, infusing x squared times x cubed to get x to the 5th or whatever. When we have the multiplying things here, I tend to not join fractions to begin with. So both versions are somewhat all for naught. Because I don't do a lot with respect to the monomial problems anyway. The majority of them are polynomial questions. Like this one, whatever. Okay. Number 25. Compare the function f of x equals that to the function g of x equals x plus 6. Okay, interesting. So 25. F of x equals 3x minus 7 times x plus 6 over 3x minus 7. When you cancel out the 3x minus 7s, you're left with x plus 6. And you have g of x equals x plus 6. So you're saying, well, they're the same. They have the same simplified form. But you have to be very careful here. This x plus 6 comes with the restriction that, hey, 3x minus 7 couldn't equal 0. So 3x can't equal 7, so x can't equal 7/3. I'm going to do a lot of those in my head, by the way. I'll say add 7 divided by 3. And you say x can't equal 7/3. That is not this restriction does not exist in my g of x equation. It only exists in my f of x equation. These are equivalent simplified expressions, except f of x has a whole at x equals 7/3. Because x can't equal 7/3 because of the original expression, and that's what matters. The expressions have the same simplified form, but the domain of f is restricted at x equals where x can't equal I have to find the symbol. X can't equal 7/3. Whereas G has an all real number domain. And I like that they have that question. Hopefully you're assigned it. Hopefully you're listening to this right now if you had confusion as to how these are different. They are different. They look like the same line in every which way, but there's a hole there at that one. Number 26. And if we were graphing later, I could show you, but I don't think we're graphing later. Number 26. Write a model in terms of x for the total area of the base of the building. An area is a base times height. So area equals 3x squared minus 12 over x squared minus x minus 20 times that. All right, they're not just saying write it. I'm sure they're saying simplify it, right? Take care of it. Okay. So we have common factor of 3. This goes into x. And over here we have that and that. Now there's one more thing I can do here. I'm going to turn x squared minus 4 right now into x plus 2 times x minus 2, so I don't have to rewrite everything else and let it sit around and wait. So this is x minus 2 times x plus 2. All right, let's see all that pans out here. X minus 2's 3 over 6 is 1/2. X minus 5's, and I think that's it. So I have a 1, wait, x minus 2. So I have 1 times x plus 2 times x minus 2. That's x plus 2 times x minus 2. And I have a 2 times x plus 4 on bottom, like so. So that is my simplified expression of this area. X is not allowed to equal 5 or 2. I gotta put the 2 first. X can't equal 2 or 5. Okay. Number 27, and I think that's it. Number 27 through 34, find the quotient. So these are the same as the multiplication problems with kind of a step before. We have to turn the division into multiplication. We do have to keep something in mind from the beginning, though, and I might do it at the end. I don't think I'm going to forget. If I do, it'll be a problem, and I'm going to change my habits. But we have to be very careful. I guess I'll circle it right now. We have to remind ourselves of this right here. X can't equal 0 from the beginning. Now, will it be a problem later? We'll find out. There's nothing to factor in these things, so we go straight into this. Now listen, don't start canceling this. Don't start doing like this stuff here. These aren't dividing. This is dividing by the fraction. We have to turn this into multiplication by multiplying by the reciprocal of the second fraction. So times 8x to the 4th over y to the 7th. It is here that we start doing our cleanup duty. For example, this y can get rid of one of those y's together, and I think that's it. 32 times 8 is 256. So you get 256. X cubed times x to the 4th is x to the 7th. Y to the 7th over y to the 7th, or times y to the 7th is y to the 14th. So we're left with that. Now notice there are no x's on bottom. Therefore, we do have to account for this thing that couldn't have been. X cannot equal 0. Not for anything that existed ultimately after the reciprocal. It's from the beginning. X can't equal 0. No x's on bottom now. We must mention it by the end. Number 28. I'm sick of the monomials. I think I do need to merge them this next time first before doing anything substantial with regard to cancellation. Just too many variables. I think you'll get too confused. Excuse me. 6 y to the 4th over 2x squared z squared. All right, remember this denominator. Pre-flip. Now we will flip 2xyz over x cubed z cubed. You know what though? Before I do any flipping, let's reduce things that we can right now. 6 over 2 is 3. X over x cubed is x squared. Z over z cubed is z squared. The z squared is on bottom, I should say. So now we have 2y over x squared z squared times, and now this flip, x squared z squared over 3 y to the fourth. Now let's multiply. Well, now this is easy enough. X squared z squared over x squared z squared are gone. And y over y to the fourth, there's a y cubed on the bottom. So I'm left with 2 over 3y cubed. 2 over 3y cubed like that. And there's a lot to take care of here. The x squared z squared, the x's and z's are gone, period. Not just in denominator. They're not in here. But they were in this original denominator pre-flip. Y still exists, and they exist in the bottom, so there's nothing we have to take care of regarding y restrictions, because the book says we don't. So x can't equal 0, z can't equal 0 based off of what we see right here. They're really prepping you for that as we move on to other problems. So although division's kind of the same as multiplication, there's still that thing you got to be careful with. All right, we start factoring immediately at this stage here. Very, very minimally. Oh, whoops, I started writing a different problem. Oh, they both have x squared minus x minus 6, that's why. 2x to the fourth, I was looking at the problem below it. Divided by x plus 2 over 4x cubed. Okay. Nothing really to do here. We will flip it. But while we do the flip, let's also do the factoring. So we can probably kill two birds with one stone there. X minus 3 times x plus 2. This is a 2x cubed we can factor out, and you're left with x minus 3 there. So as we multiply and flip this thing, we got 4x cubed over x plus 2. Now, a couple things. We will make note of the fact that x can't equal 0, and if it still can't equal 0 by the end, then we won't note it. But if we eliminate all those x's there, we'll take care of it. So x minus 3's, I think this is where we start taking care of things. X minus 3's go away. 4 over 2 is 2 over 1, and x cubed over x cubed goes away there. X plus 2 over x plus 2 goes away. You're left with, guys, 2. This equals 2. How crazy is that? That being said, everything that canceled needs to be talked about. X can't equal the 0 here, which was the 0 here. X can't equal 3, and x can't equal negative 2. This isn't saying x equals 2, by the way. This is saying this simplifies to become 2, but x can't be any of those three values. That's crazy small. Maybe number 30 being the even counterpart to this, maybe it's the same kind of crazy cleanup, which it almost feels too rewarding. You're almost like, I don't know, I wanted some x's here and there. This seems like a little too much. It doesn't feel right. Oh, it felt best. Okay. With regard to the 3x minus 3, let's just remember that for the end. No more circling those. I got a common factor of 2x on top here. On bottom, I got an x minus 6 played with an x minus 1. And we will flip this while we factor the 3 out to get x minus 1 there and 2x here. I got some 2x's that can go away, x minus 1's that can go away, x minus 6's that can go away here. I'm left with a 3, so this thing cleans up just as much as the previous one, which is awesome. X can't equal 0, 1, or 6. And hopefully you're feeling out what we're talking about there with respect to denominators. Values of x that we plug in that would give us dividing by 0 are not allowed. Number 31. We're already hitting the dividing by a polynomial, which means that number is over 1. The polynomial is over 1. So when we multiply by its reciprocal, it's times 1 over whatever. And I don't want to just call it a whatever. We're going to do something to it. So this first part here, as long as it's factorable, I shall write some factorizations, such as this. Now let's multiply by 1 over this guy. So this factors into x minus 3 quantity squared. It's a perfect square trinomial. X minus 3 is here, and let's take out one of them on bottom. And that's it. So you're left with x plus 2 times 1 all over x plus 4 times x minus 3. Now, what was before a 1 on bottom flipped over? 1 has nothing to do with our restrictions, so there's nothing I really have to talk about there. Doesn't look like anything cancels in such a way that's not still in a denominator here. So, no restrictions to mention. That's it. Number 32. Looks a lot like 31. This is a perfect square trinomial as well. So this factors into that. I got an x plus 2 here. This is times, and this is 1 over, this is x minus 9 quantity squared. So again, this is a lot like the previous question here. X minus 9s go away, one of the squared parts. They're really just, I do one, you do one, right? X plus 4 over x plus 2 times x minus 9. And just like the previous problem, the original denominator didn't have any x's in it, the over 1, so no restrictions there to mention. And nothing that canceled doesn't still exist in the denominator still, so no extra restrictions to mention. Number 33. Okay. Lot to write out to begin with. At some point I almost feel like, should I copy down the original problem? It's written over there. I do. Because it is division, I'll be flipping it over afterward anyway, so I think I'm good on that. Okay, be very cautious of what is on bottom right now. I am going to write it, I'm going to flip this, multiply it, and factor it, right? So this turns into this over this. Now, I'm turning into multiplication as I flip it. Keep in mind, what was on bottom will have restrictions to mention. I'm going to have to talk about them. I don't know the safest way. The safest way to do it is to keep this as division for one more step before you flip it over. I fully acknowledge that. I do. If it helps just for one problem here, I will write the factorization previously. So we note these are x values we can't be. If they still exist in the denominator later, then fine. But if they cancel out or if they're not in the denominator, we have to mention it. Anyway, that is x plus 4 and x minus 2 here. As we flipped it, on bottom now is x minus 6 times x plus 3. So we find anything we can get rid of here. X plus 3s, x plus 4s. Nothing else here. X plus 6 doesn't cancel with x minus 6, and x minus 2 don't cancel with x plus 2. So we have, it'll look kind of weird. Let's actually even put the x minus 6 first. X minus 6 and x plus 2 second. It looks weird. It looks cool. I like it. Now, that being said, there are restrictions here. X can't equal negative 3. We saw that cancellation. X can't equal negative 4. We saw the cancellation. And because of this, x can't equal 2. The denominator portion, x can't equal 2. It was an original denominator value that we'd be mentioning there. X can't equal 2 in that one as well. So negative 4, negative 3, and oh, by the way, the pre-flip, now new flip on 2. Number 34. We have that divided by, oops, oh my goodness, plus 13x plus 40 over. Okay, so on this one, we factor, we get x minus 8 times x plus 5. Here we have x plus 10 and x minus 2 multiplied. Okay, I'm going to flip. This bottom one's going to be on top and factored, x plus 10 times x plus 2. And on bottom, I have x plus 5 times x plus 8. All right, I saw some things that will work and won't work here. So 10s, x plus 10s, x plus 5s, and it's the same kind of thing as the previous problem, right? So here, this becomes x minus 8 times x plus 2 over x plus 8 times x minus 2. Now, x can't equal -5, -10, and from the original, this prefactor would have had the x plus 2 there, so it also can't equal -2. Now, I wonder if the book would mention those as restrictions for the -2. It can't be it, but I wonder if they're like, well, you can tell by the final, you can't tell by the final answer, it's in the numerator. You could tell from the original problem if you factored then. So I think it's worth mentioning here and now. At any point, that quantity, if it was in a denominator, you can't have a 0 out. So I'm going to mention it. I'm going to wreck it. So there's that one. X can't equal -2. Okay. Numbers 35 and 36 use the following information. Manufacturers often package products in a way that uses the least amount of material. One measure of the efficiency of a package is the ratio of its surface area S to volume V. The smaller the ratio, the more efficient the packaging. So, the smaller. When your surface area can be a lot, because surface area is your packaging material, volume is fitting more volume within there. Totally makes sense. Okay, anyway, let's go to the questions here. 35, you are examining 3 cylindrical containers, one of soup, one of coffee, one of paint. Write an expression for the efficiency ratio S over V of a cylinder. I'll just copy and paste these. So do I have to do it for all 3? I'm confused. I think we have to do it for all 3 of them. So for A, oh, I'm sorry, they're saying of a cylinder, not of these cylinders. So the cylinder surface area formula is 2 pi RH plus 2 pi r squared. The volume of a cylinder is pi r squared times h. When you divide these two things together, I mean, this is a polynomial section. This is a rational expression section. So we're doing this division. We have 2 pi RH plus 2 pi r squared over pi r squared times height. And I have a common factor of 2 pi r here, so I can be left with h plus r and pi r squared times height. I can cancel out these pi's. I can cancel out a set of r's there. So I'm left with this s over v being 2 times h plus r all over r times h. And no, nothing else there could actually cancel. So I'd be left with that on part A. I wonder if that's helpful to do anything. Oh, these are heights and radii. I didn't notice. I thought these were surface areas and volumes. Oopsie. So, perfect. We can use these now with a simplified version. Perfect. Part B says find the efficiency ratio for each cylindrical can listed in the table. Rank the 3 cans according to efficiency. So, for soup, and I know I copied pasted the table, but I can't see it anymore on my screen. So I'm going to use this formula for this. Its S over V will be 2 times its height plus its radius all over its height times its radius times its height. Doesn't matter which way we write it. I got to use the calculator for this one, so let's go to it at least for this question. And I got 2. Oh, it's not working. Hold on. Reset. All right, 2 times 10.2. All right, here's the tricky part for you if you're doing this all in one step. When you divide, put parentheses around this part when you do the multiplication. I mean the whole thing. Just do 10.2 times 3.4 straight up in parentheses. Make sure that that works that way. I get 0.784. I'll just do 3 decimal places. 0.784 surface area to volume for the first one. I don't know if that's biggest or smallest yet. We'll figure it out. Coffee. And it's good that they have, the smaller version of this formula. I'm not doing more than I need to here. So 2 times 15.9 plus 7.8 over 15.9 times 7.8. So let me just do that here pretty fast. 15.9 plus 7.8 over 15.9 times 7.8. Okay, I'm getting 0.382, much smaller than 0.784. So 0.382. Coffee seems to have a better efficiency of packaging. And then paint. Pint be all like 19.4, and these are all in centimeters, but that doesn't really matter. 19.4 plus 8.4 over 19.4 times 8.4. Okay, let me do that last one. Give me a moment. 19.4 times 8.4. Okay, I'm getting 0.341. So that's the smallest one. 0.341. So they said rank the 3 cans according to efficiency. So first, paint is most efficient, is the smallest ratio, and then coffee, and then sip. So this is most to least. And that is my final answer there. Okay. All right, that was 35. 36 is more. A popcorn company is designing a new tin with the same square base and twice the height of the old tin. Write an expression for the efficiency ratio S over V of each tin. So I don't know if simplifying this is something that I can do for these ones as well, but the surface area of a prism, well, I have both of them. I wonder if I should just, yeah. Surface area in general is lateral area plus your 2 bases. Let me just start with that. So of the smaller one, I'll say surface area, the smaller one, S sub S, is your lateral area is your perimeter of your base, the 4 S's, times your height, 4 sh, plus the area of your 2 bases. It's 2S squareds. Whereas the surface area of your larger, new tin and old tin. Let's call this new. Wait. Designing a new tin with the same square base and twice the height. So this is old, S sub O, and this is S sub N. S sub N. Did you know that SN is tin in, that's the metal, that's the, what's that called? The symbol. The chemical symbol, is that what they call it? The elemental symbol? I forget what it's called for tin. Anyway, moving on. This is perimeter of base times height plus area of both bases. So this is going to be 8SH plus 2S squared. So the volume of the old tin is area of base times height, S squared times H. And the volume of the new tin is area of base times height. So that's 2S squared times H. So the S over V of the old tin is going to be 4SH plus 2S squared over S squared times H, which you can factor an S out on top, and you have 4H plus 2S, just 2S, over S squared times H. And then an S can cancel out on top and bottom, and you're left with 4H plus 2S over SH. So there's the volume comparison there. The new tin is S sub N over V sub N, which is 8SH plus 2S squared over 2S squared H. On top, I can factor out a 2S and be left with 4H plus S over 2S squared H. 2's can go, a set of S's can go, and you're left with 4H plus S over SH, like that. All right, so we have the 2. Did the company make a good decision by creating the new tin? Explain. The difference here is this is 4H plus S over SH versus 4H plus 2S over SH. The difference is this little portion's doubled of the old tin, which means that would be a larger ratio. If the old tin is a larger ratio, because you want this number to be smaller compared to that one. So yes, they made a good decision. The efficiency ratio of the new tin is smaller than the original tin. Efficiency ratio of the new tin is smaller than the old tin. It's because of that 2 that's sticking there versus a 2 that's not sticking there. And I didn't have to actually plug in numbers to figure that out. That's just something that I could, deal with when I see the problem. Okay, number 37. The total amount I in millions of dollars of healthcare expenditures and the residential population P in millions in the United States can be modeled by these two things here, where T is the number of years since 2000. So I feel like next time I'll just copy and paste what they wrote and they'll use it later for the problems. Watch this be the only problem that has it. And P, oops, that should be a 9. 2.96. All right. Where T is the number of years since 2000. Find a model M for the annual healthcare expenditures per resident. Population is in millions, and this is in millions of dollars. I am confused. I'm determining whether I should be doing anything with respect to the millions, or if I'm good because they're both in. I think if they're both in millions, I think we're fine. So the annual healthcare expenditures per resident in 2010, that's where T equals 10. And we could substitute at any time, but we have to do this division. So I over P, except after C, is what we're going to do here. Income per person. Income in millions per millions of people. So 171,000 T plus 1361000 over 1 plus 0.018 T. Now I'm going to cheat a little bit here. They want to say divided by this thing right here, right? But that's the same thing as multiplying by 1 over this thing, which means right now I can throw this right on the bottom and multiply by that quantity here. So this can be 2.96 T plus 278.649. Without having to rewrite something again after having copied down the original problem, I can get that thrown into the mix right there, and I'll be good. So that is the model. That's the model, and then I have to substitute 10 in for T in that one, right? So I'll say I sub 10. I'll put I over P sub 10. And we have to do a substitution to figure out what the heck that number is about. So this is where I'm going to go to the calculator. I'm just going to have to type in a whole bunch of, you know what, 17100 times. Well, times 10 is going to, now why am I doing 10? Because 2010 is 10 years after the year 2000. It says number of years since 2000. 1361000. I'm computing the top first. That's how much income they make over those 10 years of this population. And then for this part here, I got to do 2 sets of parentheses. 1 plus 0.018 times 10. I mean, those things I can do in my head. I feel like I should. And then here I have 2.96 times 10. Again, could probably do it in my head. Plus 278.649. Whew. 8442.98, around $8,443 per person, given that they were both in millions. The people were in millions, and the dollars were in millions at the time. Millions over millions is just, they cancel. It's just 1, just like anything else is there. So this is the annual healthcare expenditures per resident. Per resident. Annually. Okay. That's number 37. Number 38, the total amount I in millions of dollars, I'm probably going to copy and paste this one, of school expenditures from pre-kindergarten to a college level and the enrollment P in millions in pre-kindergarten through, so they're both in millions again. We can just set it up like that. Can be modeled by these two things, and I'm bringing them in. This is probably just a lot like 37. T is the number of years since 2001. Find a model M for the annual education expenditures per student. Estimate the annual education expenditures per student 2009. 2009 is 8 years after 2001, so we're going to do T equals 8 there. So our I over P in this case will be, it's going to look the same, just different numbers. 17913T plus 709569 all divided by, and we have this quantity that's going to multiply by this other quantity here because it's dividing by the set, it's multiplying by its 1 over counterpart. Like this and that. Okay, so that's the model. Now we got to substitute 8, and 8 isn't as easy to substitute as 10. See, 10 would have just been easy decimal shift. Not that I could have calculated all that at the time, but I am substituting 8 now into this thing. So let's go back to the calculator. We got to type brand new numbers here. We have 17913 times 8 plus 709569. That's the top. And then divided by, in parentheses, I got 2 sets of parentheses I need. 1 minus 0.028 times 8. And then another set of parentheses, 0.5. Is that 0.5906? I got to read it. My handwriting on mine's bad. 0.5906 times 8 plus 70.219. I hope I didn't make a mistake on numbers because I won't know. So $14,665 about per student. Remember, these were both in millions, so when you divide the millions, they cancel. So $14,665 per student. All right, for those 8 years. Okay, number 39. Excuse me. Using equations. Refer to the population model P in exercise 37. Interpret the meaning of the coefficient of T. Interpret the meaning of the constant term. 37 was this guy up here. For the coefficient, I'm sorry, I'm looking at which one? Oh, the model P. I was like, which one, which T do they want? So they want this bottom one. Okay, they want this one here. So the T, the coefficient is 2.96. Now this population was in millions. So I guess we multiply it by a million and it says 2.96 million. 2,960,000 people. So that's how many people, this is population. This is how many the population is increasing by each year. So on number, okay, so I have them right here. So it's right there. So the population is increasing. It's 39. Two 960,000 people each year. Residents, really, but because that was millions, right? And then they said interpret the meaning of the constant term. That's how many people there were in the year, was it 2000? Number of years since 2000. This is how many millions of people there were in the year 2000 in that sentence. So part B, I'll write in a second, the population was, this is million, 278,649,000 people in the year 2000. That is part B. So that's the interpretation of both of them. That's the millions. Okay, is that it? I think so. Number 40, how do you see it? Ooh, graphs. Use the values of f and g to determine the excluded values of the functions h of x equals f times g of x and k of x equals f over g times x. Oh, that reminds me. I probably should have used parentheses here and here for those ones. Explain your reasoning. The excluded values, oh, those are f and g. I thought this was the times and the divided by or something like that. All right, so with respect to this one, there is a vertical asymptote. Oh, I want a dotted one. So this kind of goes back to our graphing things, right? So there's basically a vertical asymptote here. These are scaled by 2, so that's at x equals 1. Don't worry so much about the horizontal asymptote. At least I don't believe there's any reason to think about that one. But this one, x can't equal 1 for f of x. For f of x, x can't equal 1. for g of x, we good. G of x, no restrictions. Now they're talking about, however, what I think I need to bring up is what values of x give me 0. So actually, here we go. The x-intercepts, because we're going to do f divided by g of x at some point. So forget the no restrictions part. X-intercepts, the values of x that give me 0 are -4 and 1. So when we do h of x equals f times g of x, excuse me, we still have a restriction on 1. Basically, we're dividing by an x minus 1 somewhere. So here, x can't equal 1. That's for the same reason that it doesn't matter if we're multiplying by something with the g. It gives me a 1 there. It would have a canceling out effect on those things. I plug in a 1. This has an x minus 1 and x minus 1. They cancel out. That doesn't mean there's no restriction there. So that's definitely a huge part. The other one is k of x. And that's f over g of x, excuse me. Where now you have f of x has an x minus 1 on bottom. G of x has an x is on the bottom, so there's an x minus 1 there as well. So there are two sets of x minus 1s. So -4, x can't equal -4 here. I'm trying to decide if I should stick to saying x can't equal 1, though. It's one of those things where it's in the denominator. It's x minus 1 squared even. But it's one of those things that they don't bring up because they don't. Excluded values. Their version of excluded values or restrictions is not anything in the domain. It's just things with holes. I got to think about what they'll say here. I want to say x equals 1 doesn't work. I'm going to say x can't equal 1. It's the idea that it exists in the denominator of this function. It's in the denominator of this function right here as well. So despite the fact that it appears there, I'm stating it. Sorry if the textbook's mad at me. Number 41, drawing conclusions. It says complete the table for the function here. Like we're graphing again suddenly. So y equals x plus 4 over x squared minus 16. Now note that we're not simplifying this. They said complete the table. There's a reason for that. Use the trace feature of the graphing calculator to explain the behavior of the function at x equals -4. Okay, so there's a whole thing behind this. They're talking about things like limits. You probably don't know what limits are because you're not in pre-calc, but you might have seen Mean Girls where Lindsay Lohan's character Katie goes, the limit does not exist. Here, there is an existing limit, and we're going to figure out what that limit is by substituting this. So we're going to do x plus 4 over x squared minus 16. How unprofessional, Mr. Robinson. And use the trace feature on the graph. Use the trace feature? I'm going to use the table feature. Oh, it says complete the table first. So in the table, let's get some of these values in. We're going to have, oh boy, I'm just going to write down what I see. -1.33 or -0.1333. -0. Oh, I have the wrong values. I'm sorry. They have really random values here. I didn't even notice that. Let's just ask, and let's do these ones. So I have -3.5. I already plugged that in. -3.8. -3.9. -4.1. All right. Sorry. Okay. So -0.1282. Okay. So I put these ones in here. They're stating, use the trace feature of a graphing calculator to explain the behavior at x equals -4. So the thing is let's go back to the graphing calculator. In the on the graph, and we really probably have to zoom in at that -4-esque area, right? We're going to have to go over here and kind of figure out what's going on around that area. That's what they want us to do. So I'm going to zoom in. And you can't see any issues with this as a whole. I don't know if it lets me actually hit -4. See, that's the problem. The trace feature isn't telling me very much. What I want the trace feature to do is tell me what happens when x is -4. So I'm going to use the value button. I'm going to plug in -4. Look what happens. Y equals doesn't show anything. I actually thought it would say error. But y doesn't equal anything there. If I went back to ask and I plugged in -4 here, I think here it'll say error. The problem with this equation, despite the fact that x minus 4's cancel, and then you're left with, by the way, 1 over x minus 4, x still can't equal -4. They're showing you this. X cannot equal -4. But what is the graph showing you? Graph is showing you a whole lot of points. It's zoomed in, but it's showing you points. It doesn't show you an issue there. The graph has trouble identifying holes, really. But there's a hole there. There's a way for me to do it. Let me do my -9.4 window range thing. Let me see if I can get there for you. Otherwise, that's just my way of mentioning that it doesn't show your points there. All right. So here's the graph one more time. Trace. Here we go. Watch this. Boom. Nothing there. To this side of it and this side of it, we all good. We saw that in our table. Right there, nothing. So there is a hole. There's a hole, and it looks like, you notice here, this blinks, it blinks, and right here, it does nothing. And then it blinks again, and here it does nothing. So really interesting how it goes about that. So this is just like this graph. This is just like this graph, where this is shifted 4 units to the right and all that kind of stuff, but there's a hole at x equals -4. I lived on this problem way too long already, so how do I answer it? Explain the behavior of the function. It is not defined at x equals, it doesn't have a value. It doesn't have a value. X equals -4, but it is approaching something. The limit is approaching something, but the graph approaches y equals, I didn't tell what it approached. Let's see. -0.125, -1/8. And actually, that makes a lot of sense. I'll show you that. -0.125 at that value. That's what we call a limit. How can I tell it approaches that value? I can still substitute. Even though x can't equal -4 in the original equation, I can substitute it in the simplified one to see what it would have been approaching. 1 over -4 minus 4 is -1/8. You know what -1/8 is? -0.125. So I'm educating you on something you won't learn till pre-calculus probably, or calculus, but that's what we do with limits. The limit does not exist, but there it does. Number 42. Making an argument. You and your friend are asked to state the domain of the expression below. Your friend claims the domain is all real numbers except 5. You claim the domain is all real numbers except -9 and 5. Who is correct? Explain. See, it's a problem like this. This is where I get upset with the book. It's a problem like this where now we're not talking about exclusions, but we're talking about domain. Maybe that's the difference. Maybe there is actually a difference between the word exclusions and restrictions. That being said, domain restrictions are what I want to refer to. So listen, when this thing factors, it becomes x plus 9, x minus 3, and on bottom there's x plus 9 times x minus 5, like that. Now x plus 9's cancel, so you're left with this whole x minus 3 over x minus 5, and what we would have written before was x can't equal -9, and we would have just been done like that, right? But that doesn't answer the question. This says your friend claims the domain is all real numbers except 5. They're probably talking about that because you can't divide by 0. You claim the domain is all real numbers except -9 and 5. Who's correct? Explain. It's interesting. I thought they would have said your friend claims it can't be anything. It can be anything but -9. Now it is -9 and 5, but both numbers are restricted, are excluded from the domain. Both -9 and 5 are excluded from the domain. Original equation. It would lead to dividing by 0. A 0 in the denominator. Now notice in our answer, why didn't you write x equals 5? Exactly. The book doesn't care for us to write. I get, I've stated this before and I'll keep stating it again. I get that they're having us state this one as a for sure, because it's gone from our set. They're saying, oh, by the way, ha ha ha, and here we can infer it. I get it. But now they're actually asking about domain, and I don't want you to forget that x can't equal 5 as well. So anyway. Okay, number 43. Find the ratio of the perimeter to the area of the triangle shown. Ooh, okay. So in this one, we have to find that perimeter by doing a bit of Pythagorean theorem stuff. I want to copy it over, but there's text that will get into the way, so I think I have to redraw it. So I got an 8x, 6x, and 15x. Let's first just talk area. Area is 1/2 base times height. Half of 8x is 4x. 4x times 21x is 84x squared. There's our area. Perimeter is going to take a little bit. Actually, it's not going to take much. This is a 3, 4, 5 special triangle, and 6, 8, 10, and that is x. And 8, 15, 17 is 17x there. So your perimeter is, that's Pythagorean theorem in a nutshell, 10x plus 17x plus 21x, the combination of the 6x and 5x. And there you have 48x. 48x. Okay, so find the ratio of the perimeter to the area of the triangle shown. So perimeter over area is 48x over 84x squared. This x can go, one of these x's can go, and 48 and 84 can each divide at least by 4. You get 12 over, oh, we can divide by more than that. So I guess you can divide by 12. Yeah, you can divide by 12. So you get 4 over 7x, like that, 4 over 7x. No restrictions on x. Well, there's a restriction. X can't equal 0. It couldn't anyway for the lengths, but it's in the denominator, so we don't have to mention it. Okay, number 44. Find the expression that makes the following statement true. Assume x can't equal -2 and x can't equal 5. Okay, so let me just copy and paste this. So for this to work out, we're going to have some things cancel. Now it's a division problem. It's a division problem, so we are going to be flipping the second fraction here to make this thing what it is. So let's figure out more on this thing. X minus 5, x plus 7, x minus 5. So here we have some x minus 5s that go. So they're already gone. So x can't equal 5 is a part of it. This guy is going to go up top. This is x minus 5 times x plus 2. Now, what needs to be on bottom for the x minus 5s to go? And that's it, just for x minus 5s to go. Well, x minus 5, like that. So if this one goes, now you have x plus 2 over x plus 7. X plus 2 over x plus 7. Now they said assume x can't equal -2 and x can't equal 5. Well, it can't equal 5 despite the cancellations it can. And it can't equal -2 because this was on bottom. This was a factor on bottom before, so that's still a part of it. So that answers x minus 5. In exercises 45 and 46, perform the indicated operations. Oh, you have multiple things going on. Okay, a multiplication and a division. How about that? We have 2x squared plus x minus 15 and a larger set of quadratic things with 2's. And 2's not a common factor. Ooh. 6x plus 9, just as its own. It's over 1, but whatever. 2x minus 5 over 3x minus 21. Okay. So let's do some factoring to begin with. We got 2x, it's been a minute since I've done these, plus 3 and minus 5 would be 6x minus 5x, which is 1x. And then here, this is going to be 7 and 3, minus minus 7 plus 3 gives you negative 14 plus 3 is negative 11. So that's good. And then this is 6x. Oh, there's a common factor. Common factor of 3. So we got 3 times x plus 2x plus 3 all over 1. And then I can multiply here as I flip this. 3 is a common factor to get x minus 7. And this is still a 2x minus 5. Nothing can factor out of that. So 2x minus 5. That being said, I'm going to cancel out some things that I can cancel out. So I do have x minus 7's here. I do have 2x plus 3's here. I have 2x minus 5's here. And I'm left with 3 times 3, which is 9, times the x plus 3. So I'm left with 9 times x plus 3. You can write it like that or distribute it, whatever. This is over 1, so I'll leave it like that. Now, there were a few restrictions here. What were they? Among them, x couldn't equal, 7. If I add 5 and divide by 2, x couldn't equal 5 halves. And if I subtract 3 and divide by 2, x couldn't equal negative 3 halves. Now, how about this one before the flip? Oh, that was 7, so we're good there. So those are the 3 that it can't be. Okay, number 46. We have a sum of 2 cubes and x cubed plus 8. They trying to be fancy. They didn't fool me. X cubed plus 8 times. That can't factor. So I'm guessing that has to do with the sum of 2 cubes here. Only a guess. In fact, only 2 things here can factor. So x cubed plus 8 is x cubed plus 2 cubed. So that factors into x plus 2 times x squared minus 2x plus 4. Yes, that's the same thing as that other one. This is all over 1 if you'd like to write it like that. This is still the same as it ever was. And this multiplies by, this is x minus 6 on top now. And on bottom, factored is a difference of 2 squares, x minus 2x plus 2. Okay. X squared minus 2x plus 4's are gone. X minus 2 here's are gone. X plus 2's are gone. You're left with x minus 6 all over 1, which is x minus 6. Because everything that went away is going to have restrictions we got to mention. X can't equal negative 2. And x can't equal positive 2. The x minus 2 is also. So x can't equal plus or minus 2. The x squared minus 2x plus 4, I've mentioned this before in the sum of 2 cubes. No real solutions. So there's no value for x I can plug in that's real that would get me 0. So I don't need to mention them. It's just positive and negative 2 that are the things there. Oh, the x minus 6 was in the denominator. So now also that one. Let me separate these then. X can't equal negative 2, positive 2, or positive 6. Despite, you're like, oh, what about here? It was originally in the denominator. Okay, number 47. Animals that live in temperatures several degrees colder than their bodies must avoid losing heat to survive. Yes. Animals can better conserve body heat as their surface area to volume ratios decrease. It's like the packaging efficiency. Find the surface area to volume ratio of each penguin shown by using cylinders to approximate their shapes. How shapist. Body shaming. Which penguin is better equipped to live in a colder environment? Explain your reasoning. Okay. So the Galapagos penguin has a cylindrical height of 53 centimeters and a radius of 6 centimeters. So can we still use... Oh, what are the other formulas? Can we still use this? These were cylinders. I'm going to copy and paste that thing. Because this, listen, it was a quicker way to do surface area to volume, right? So let's use it. So surface area to volume of cylinders goes like this. So for the Galapagos penguin, our surface area to volume will be 2 times height plus, that's a 53, plus radius over height times radius. 53 plus 6 is 59. 2 times 59 is 118. 118, using the calculator now, 118 divided by 53 times 6 is 0.371. 0.371 surface area to volume. The kingpin penguin is about surface area over volume. 2 times 94 plus 11, not drawn to scale, of course not, over 94 times 11. 94 plus 11 is 105. 105 doubled is 210. So 210 over 94 times 11. 210 divided by 94 times 0.203. So that is a smaller surface area to volume ratio. So the king penguin has a smaller one, so it's better equipped to live in a colder environment. Not kingpin, the king penguin has a smaller All right, so that was a lot like that other question. In fact, I got to use that other formula, which was kind of nice, kind of sweet. All right, 2 more questions. Number 48, thought-provoking. Is it possible to write 2 radical functions whose product when graphed is a parabola and whose quotient when graphed is a hyperbola? Justify your answer. Ooh. I can't think too big on this one, otherwise I'm going to mess up. If I did root x times root x, I get x. So let's just do something that's bigger, but they got to stay as radicals. Would root x squared count as a radical? I don't think so. I don't think they count that. So how about root x times root x cubed? What if I did root x times root x cubed, because that's root x to the 4th, which is x squared. So that's a parabola. Now, would that leave me with a hyperbola in the other sense? If I did root x over root x cubed, that's 1 over root x squared, which is 1 over x, which is, yeah, that's a rational function, so hyperbola. So I believe those are 2 radical functions we can do. So root x times root x cubed, root x divided by root x cubed. I'm going to leave it like that. I'm not going to speak much on those. I thought that was going to take longer, and I think I lucked into an answer. Number 49, reasoning. Find 2 rational functions f and g that have the stated product and quotient. How about the one we just did? All right, so in 49, f times g of x equals x squared. That could be anything. F divided by g of x equals x minus 1 squared over x plus 2 squared. Okay. This x squared obviously is 2 x's that multiply, but it could have the x minus 1's cancel on these things. Remember, the f times g of x means f of x times g of x. If I had an f of x times g of x like split, we could have this as, like blue and green. In blue, if I had an x on top and, I need the x minus 1's, an x times x plus 2 over x, x, which way does it have to go? X minus 1 over x plus 2. And then I'm multiplying it by a g of x that also has an x, but then this is an x plus 2 on top and an x minus 1 on bottom. X minus 1 on bottom, what would happen is the x minus 1's would cancel. The x plus 2's would cancel, and you'd be left with x times x, which is x squared. So that would work out. The f divided by g of x, does that work? We would now do f of x divided by g of x, and there we would do, will this work? Where we would do x times x minus 1 over x plus 2, and then divided by, we multiply by the reciprocal. Okay, I want to get straight in that. And guess what? The x's would cancel. We do divided by, times the reciprocal, which is times x minus 1 over x times x plus 2. Are they in the right spots? The x's go. I didn't think about that. I'm glad I made them go. X minus 1 is x minus 1 squared. Yes, that does work. So I can make my f of x as my final answer. My f of x will be x times x minus 1 over x plus 2. And my g of x would be x times x plus 2 over x minus 1. Now, they didn't state restrictions. They should have stated restrictions on these. See, that would have been nicer. We did that for every problem. They should have done the excluded values. There it is. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Multiplication and division should be easier than addition and subtraction all told, because now we got to seek common denominators, and there's more to do with them. I actually hope they do something on these problems to make them clean up a little bit more. Whenever I write test questions for addition and subtraction, they can get a little tricky. We'll see how they go. Thank you guys so much. Take care. I'm going to see you in the next one.